Now we're going to practice drawing some ionic Lewis structures. With ionic Lewis structures, we have to keep in mind that ionic bonds are non-directional. So each positive atom is going to be attracted to each negative atom that's surrounding it. For that reason, we can't draw a whole ionic compound. Instead, we draw what are called formula units. So a formula unit just shows you the ratio of positive to negative ions in a complex. So for instance, if you have NaCl, that tells you for every 1 sodium, you have 1 chlorine. That would be your formula unit. Or on the other hand, let's say you had BaCl2, barium chloride. For every 1 barium, you have 2 chloride ions. So the formula unit just shows you the lowest whole number ratio of positive to negative ions. The other thing is that since these bonds are non-directional, we don't show them by drawing a line, for instance, between Na and Cl. We do not do that because those electrons don't sit between sodium and chlorine. Sodium and chlorine aren't sharing their electrons. So let's see how to draw these Lewis structures in a way that accurately represents an ionic bond with these non-directional bonds between charged ions. The first thing we're going to do is draw Lewis structures of the neutral atoms. We've already seen how to do that really easy. We just count the valence electrons. Then we're going to move electrons from the metal to the nonmetal. Each of these wants to form an octet, but they do it differently. The metal forms an octet by giving away electrons to empty its outermost shell. A nonmetal forms an octet by gaining electrons to fill up its outer shell. It's not always a 1-to-1 ratio, so sometimes we actually have to put in more metal or nonmetal atoms to make this happen properly. Finally, once we've figured out how many of each ion we have and we've drawn their Lewis structures, we're going to draw them next to each other, and we're going to remember that the ion always goes in brackets. We always put charges on those, and we use coefficients to indicate how many of each ion are in the formula unit. So let's look at a couple examples. We'll start with barium oxide here. So the neutral Lewis structures, we have Ba, we have O. Barium has 2 valence electrons, whereas oxygen has 1, 2, 3, 4, 5, 6. Now again, we're not going to draw a line or a direct bond between the two atoms because ionic bonds are non-directional bonds between charged particles. So we're just going to start transferring electrons from the barium to the oxygen until everyone has their octet. So the barium can put 1 electron right here, and you can put another electron right there. And we see now we have a barium. He gave away 2 electrons, so he has a charge of +2. And we have an oxygen who now has a full octet. With those extra 2 electrons, it had to gain 2 electrons to do that. So it has a -2 charge. And we just draw those ions next to each other to show for every 1 positive barium ion, there's 1 negative oxygen ion. All right, let's look at another example. Let's try barium chloride. So now we have 1 barium. We have 2 chlorine atoms. So barium has 2. Each chlorine has 7 valence electrons. Now this time, barium can put 1 electron on this chlorine, but then this chlorine has his octet. He's completely done. He doesn't want anything else. Then we can move this other electron to the other chlorine. So now both chlorines have a full octet. They're both happy, and barium's given away both of his electrons, so he's happy. So we want to condense that. We have our barium that has a +2 charge because he gave away 2 electrons. Now we have 2 chlorine atoms. Each one has achieved an octet by gaining an extra electron. So each one has a -1 charge, and everything has an octet, so everything's stable and happy. And this shows that for every 1 barium ion, we have 2 of these chloride ions. Now, in the first 2 examples, it told you the ratio between the 2 atoms, but that's not always the case. So let's look, for instance, at this second problem. Draw Lewis structures for the compound that form between potassium and nitrogen. So we'll start with just 1 potassium, 1 nitrogen. Potassium has 1. Nitrogen has 5. And we can see that, all right, potassium wants to get rid of his electron. We can put it right there. That still gives nitrogen only 6 valence electrons. So what we need to do is bring in another potassium who can put his electron right here. But now nitrogen still only has 7, so we need a third potassium that's going to come in and give his away to give nitrogen his octet. So we've had 3 potassiums, and each one has given away 1 electron to become a +1 charge. And we have a single nitrogen that has finally achieved an octet, and it had to gain 3 electrons to get there, so it has a -3 charge. That should be a 3 there, not showing up very well. So 3 positive potassium ions for every 1 nitrogen. All right, let's look at another one with aluminum and sulfur. So again, we're just going to have to figure out how many of each we'll need to achieve these octets. Aluminum has 3 valence electrons to start with. Sulfur has 6. So we'll do the same thing. So aluminum can give 1 valence electron here and 1 valence electron here. So now this sulfur has his octet. But aluminum's not happy because he still has an extra electron. So what we need is we need another sulfur, which has 6. And now aluminum will give his last one away right here. So now that aluminum's happy, but this sulfur isn't happy. So what we do is we bring in a second aluminum that has 3. We say, all right, now you're going to give yours away right here, give you an octet. So now this sulfur's happy, but now this aluminum isn't. He has these extra 2 electrons there. So we bring in yet another sulfur who has 6. And now aluminum can give 1 electron right there and 1 electron right there. It's a little messy here with how I'm writing it, but we get the general idea. We need 2 aluminums to give away a total of 6 electrons to 3 sulfurs. Each of them gains 2 to give a total. They gain a total of 6 electrons. So ultimately we have 2 aluminums, each of which has a +3 charge because they all gave away 3, with 3 sulfurs, each of which has a -2 charge, and each one now has an octet. So we need 2 aluminums for every 3 sulfurs so that we can get these octets and get a stable ionic compound.